All right, look, I know they ran late. I've had a lot of coffee, so I'm going to speak a lot faster than I generally do, and then we can all go for a drink. So I'll be very quick. So I'm Revikumar. I'm originally from India, spent some time in the US, went to Australia, now I live in Geneva. That for me is improbable in by itself, right? If somebody asked me 10 years back what my linear curve would have been, this would have not been there. But CERN is the place where I wanted to come because in so many ways, CERN is the heights of improbability, right? So I'm going to give a little bit of story about CERN, what we do, why we think startups, I'm kind of going to be preachy to you all because by definition, if you're pursuing a startup, it's improbable. So a little crazy, you have to go pursue it, and our job is to support. So if I tell you I want to build an accelerator to smash things just because we don't know what's inside of stuff, and I tell you it's going to cost you tens of billions of euros to build, and about €1 billion to run every year, people would say, not likely going to happen, right? And for me, this is why it's fascinating what we've built. And this is the aerial view of CERN. What you see in the background is the beautiful Swiss Alps. That's Lake Geneva. And that yellow ring is the world's biggest machine ever built. It's the LHC, the Large Hadron Collider. Large because it's 27 kilometers in circumference. Hadron because we use ions and protons in the accelerator. They belong to the Hadron group. And Collider because we collide them, right? At these 4 points, ALICE, ATLAS, LHCb, CMS. I'll go into a little bit more details. So for me, when I moved to Geneva, family back home thought I worked for the UN, right? Because you always associate Geneva, all the UN agencies. I mean, nothing against the UN, but I'm an engineer. I don't want to be associated working for the UN. So I had to explain what we do to my mom. And that was the hardest challenge. And so without going into particle physics, the best way I could explain was, if I give a 5-year-old 2 balls that rattled and told him, find out what's inside, intuitively you'll smash it to find out what's inside. That's exactly what we do, right? So we've built this one as a toy for all the physicists in the world who can come and test their theories. So we are an infrastructure provider. We have the biggest machine, the particle accelerator, so scientists can come and play and test their hypothesis on the beamlines. Why do I think it's improbable? All our detectors, I'm going to go show the photographs of all 4 of them. This is ATLAS. This is 100 meters down, weighs about 15,000 tons. And the 8 stuff that you see around, this is during constructions, are the largest magnets before ITER was done. So these are large magnets which can hold the beam inside and make sure they collide. Just to give you the scale of it, that's a man standing next to it to give you the size of how big it is. This is one of the detectors. The best way to think about these detectors are these giant 3D cameras. Right? So we get these 2 beams to go opposite directions and we make them collide. And these detectors have millions of sensors so that they can see how these particles move. This is called the compact muon solenoid. It's about 30 meters in diameter. So there's nothing compact about it, but that was the first solenoid that was ever built. The previous ones were all theoretically impossible to do. Third one, this is ALICE. The red things that you see is actually part of a magnet that closes. It takes about 3 weeks to close because it's so damn heavy, but now it's closed because the experiments are running. And the last one is, this is LHCb, LHC Beauty, because we look at the B quark in this, and this was one of the smallest ones, but it's a vertical detector where we collide it to see how the particles go. The thing is, we are not that only the LHC, it's a series of accelerators, complexes that go in. I'm not going to talk about particle physics, a standard model, but just to give you how improbable it was, the history of CERN was in 1956. It was set up because after World War II, the physicists all left Europe. We wanted to build something so big they can all come back to Europe, and this was it. And 1969 was the first detector that was, or the accelerator that was built, because the theory was there's this particle called pion. And when it decays, it produces one electron and one neutrino. It was all theory. Nobody's ever done that. We built it. On the first day, we proved that that theory was correct. This was about 60-year-old theory, right? So you need these massive engineering marvels to happen to build things like that. So just to, I did lie. I'm going to talk about particle physics for just a minute. So we start with a bottle of hydrogen, strip out the electrons, you get proton. It goes to the first loop, goes to the second loop. It goes to 99.99% of speed of light there. And after that, we keep putting more energy and making it go around before it goes to the booster and goes to the LHC. It can't go any faster because it's a 99.9999% speed of light, and so it gets heavier. So more heavier, and you collide something, you'll get more particles out of it. So at least that was the theory when it was built or proposed in 1970. At that time, none of the technology existed to make this happen. So that was the biggest leap of faith of about $30 billion to commit, to dig tunnels for 27 kilometers, put the biggest superconducting magnets. For me, I am always amazed that that level of commitment and taking that risk to build this, if it failed, everybody would have said, I told you so that this wouldn't work, right? And so for me, to make something build at this scale is no different than what most of you are going through as startup founders, because everybody said, this won't work. And now, I'm not going to go more into details. There's a ton of experiments that work here. Just to tell you about Atlas, where I said the Higgs boson was detected. 6,000 people work on that one experiment globally, right? And so the paper that was published when Higgs boson was found had 6,000 authors as acknowledgement. So there's 3-page paper, technical paper, and 20-page with names. So now the question is, why do we do all of this? The simple answer is we want to know stuff that we don't know, to push the fundamental knowledge of what we are made of, why universe exists, what happened after Big Bang, right? And the question we get asked, like, all of this money to that, we think it's important, the basic knowledge, right? One of the things is on antimatter research that we do. We have a place called Antimatter Factory where we slow down particles and understand. The theory is, after Big Bang, there was equal amount of matter and antimatter. And you all seen Tom Hanks in Angels and Demons that, blows up Vatican. We don't do that, but that's the idea. So they annihilate each other. If that theory was true, then we should all not be there. The chair shouldn't be there because it's all made of matter. It should cancel each other out. So the theory is there was more matter than antimatter, and we have to prove it. So recreate the entire situation, how it was after Big Bang, to prove this. Again, researchers, we have trapped it. We've proven the first thing, saying that there was more matter. And so these are fundamental questions that we don't know. What is gravity? Why does gravity happen? Why do particles have mass? These are fundamental questions that we want to prove. But in that process, there were people crazy enough to think they can change the world, and they ended up doing so. For me, is Sir Tim Berners-Lee, right? We all use World Wide Web because he made a proposal, came up with HTML. For me, the beauty of that was we didn't patent it. We didn't make it not just open source. We made it public domain that nobody can ever claim ownership to it because it was so much bigger than one person owning it or one person using it. For me, this quote is a lot of ways what defines scientists. Why would you pursue curiosity-driven research, or why would you pursue startups? And every improbable startup was because founders, I took the crazy out, and the technology that enabled them, right? For me, always basic research gets put in a bucket that, it's scientist mumbo jumbo. Why would we care about it? Because we are building apps around it, or a marketplace, or SaaS, et cetera, et cetera. For me, it's the core enabling part of it, right? So let's take Instagram. Instagram was awesome. We all put photos on it, video, reels, all of it. That was enabled because we had cameras, right? That was because there was a CCD invention which won a Nobel Prize. Then came CMOS sensors, We made our silicon, which is cheaper than sand. Apple took it and put it in every phone. We all bought phones. We all took photos. We have to share it and show off. So Instagram was built 20 years before of that invention of that sensor. So for me, whatever we are creating now will not have an immediate impact, but that will be the base on which the next generation of startups will come. And that is where the improbability of those inventions come in, right? And some of the founders we support at CERN are these people who push that envelope of what science can do now, right? And we've got amazing laser technologies that's coming out, which can revolutionize how we use LiDAR to sensors, laser-driven sensors. So our aim is to have those and give it to people who are crazy enough to saying, okay, let me build an application for this out of it, right? So one part of it is to support the founders at CERN to saying, yes, go for it. And the other is support startups to saying, look, we've got this cool toy. We don't know what to do with it. Do you want to do something with it, right? And so that's the two angles that we play. And for me, it was always the improbability of the deep tech part is not because it has to be something super fancy, billions of transistors. We all know this, right? I wanted to take one, but I forgot. So bear with me. This is a sticky tape we all have in the office. But I'm going to tell you that this is the cheapest X-ray generator in the world, right? So when you take the sticky tape and you go, that sound, every time you do that, you get an X-ray out of it. Google sticky tape X-ray, you will get a video by UCLA researchers who proved it, right? There's a Nature video talking about it. But it wasn't something new that they came up with as well. It was a Russian physicist who in the 50s was stripping mica out and he found X-rays in it, right? So this, you would think, well, nobody did anything about it. It was caught and stuck and collecting dust. Now, the postdocs did make a spin-off, raised money from Founders Fund, i.e. Peter Thiel, Founders Fund, got together an executive management team, which was fantastic on paper, built an entire device, a semiconductor version of it so that you don't run out of tape, which actually works, made a product, got money from US Army, did all of that, and they still failed after raising 15 million 20 years back, So irrespective of what happens there, you have no control of why a startup wins or loses, whatnot. For me, this is improbable tech, something which is so simple, curiosity-driven, and saying, why do we get this? And then seeing how we can do it, right? When you do pull that X-ray, or to the X-ray machines or the sticky tape, you get enough X-rays to make, they took one of those dental X-ray things, put it on top of their hand, and they saw the image of a finger, because you put it on top of it and you'll see it. That, for me, is fascinating, right? So somebody is saying, why is that sound coming when I make that thing? There should be something because you're peeling off electrons or you're peeling off an energy level. The curiosity-driven research to look at the basic fundamental of things and saying, why is this working, is, for me, what removes that improbability of everything, and science helps you understand, helps you repeat it. I told folks yesterday over dinner, for me, there are two things which is universal. It doesn't matter if I do that in India, in Estonia, Australia, wherever. One is music. It's the same everywhere. You play a violin here, it's going to sound the same in Switzerland as well. Second is science. Whether you do science here, science in Geneva, or science in India, it is reproducible. Nobody can BS about it. So for me, science helps remove a lot of those improbabilities. And two messages I want to say before I say thanks is, one, CERN has a lot of technology. So if you're a startup and you're saying, well, I want to look at something tech, come talk to us. And you're happy to connect with the scientists who can give you the answers on whether it is, you're building something with superconductors, or if you're a quantum startup, we kind of understand quantum physics a little bit better than others who speculate. So on that, thanks for having us here. Happy to answer questions. I'm 5 minutes early, so we can go for the drink earlier.
Thank you very much for this amazing speech and talk. I have a question. First of all, give a big thanks to CERN for World Wide Web. But now the next generation CERN, which has 3 times large the diameter, will we be able to see the dark matter?
Yep.
And even dark energy?
Mm-hmm. So one of the big research fields is exploring dark matter, dark energy. What does it mean? If you can't see dark matter, how do you recreate it, right? So the 2 things that we're building, one right now which is happening is called the High Lumi project, where we've increased the energy of what we put 10x into the existing infrastructure. What's planned on the thing is a 100-kilometer circumference, which goes all of Switzerland now, to pursue those questions. Right now, we can't with our current infrastructure, current experiments we are planning. That's the next bigger question of how does dark matter exist? How can we capture? How can we analyze what happens? So I don't know the answer. At that point, my physics understanding is over my head. So, but that's what we're looking at. That's one of the big research questions for us.
Any more questions?
Yeah.
Thanks a lot for inspiring.
Cheers.
Understanding is about asking questions. Mm-hmm. Whether you believe science is the abstraction or fate is the abstraction. So I'm asking you, have you seen that you also are improving on how you ask questions into probabilities of matter or science to find the answers more maybe accurate or at faster speed?
So, I mean, let me give you, rather than predicting future crystal ball, I'll tell you what happened before. So the Higgs boson was predicted to have this particular energy bump, right? And so we run the experiments nonstop for 2 years. So every billion collisions, you will get 1 Higgs boson. That was what the prediction was. So we make 40 million collisions per second. So when we run it for 2 years, we collect all of the data. And so when all 4 experiments are going, we generate 4 terabytes of data per second, right? And so even if we had all the money and all the storage availability, we can't store all the data. So we have to downsample it 99%. And imagine throwing the data which had the Higgs boson. That would be like a big blunder. So we invented our own machine learning FPGA algorithms, which is implemented on-site at level 1 trigger, which uses a trajectory map to saying which data to be kept. All of that background to saying that the data that we got was 6 sigma equivalent, 125 giga-electron volt is where we know a Higgs boson would be there. We have to have multiple data converge on a 6 sigma variance before we published it, right? And so it goes through a massive peer review of 5,000 people, 5,000 scientists agreeing that it exists before we publish. So we are massively fact-driven, massively driven by questions, and that's what keeps us truly honest is we say something exists, right? So by the way, Peter Higgs proposed this 40 years back. He had to wait 40 years to prove his theory. Physics is only, theoretical physics is probably one of those fields where you have to wait 40 years to prove what you said was right or wrong, because all your predictions was based on mathematics to say, yes, this should exist, but we don't know. So we had to do those experiments to saying that existed, right? And then where it really messes up my head is that all of I'm talking about is particles actually colliding. So in my head, it was like little things going, right? But then comes the quantum field theory on it. It's like, it's not really a particle, it's an energy, and another energy coming, and then going to another energy level. And that's where you go really fast, right? So don't ask me about quantum theory, but I can stick with the particle visualization. Hope I answered your question. Yeah, cheers.
Did someone raise a hand? One last one? Who's the brave one? Nope. Nope.
Cheers. Thank you.
Thanks, man.
Hey, cheers, man.
Thank you.
Cheers.